Hello and welcome from the OPC Foundation. My name is Stefan Hoppe and I'd like to welcome you to today's webinar about the results of the OPC Foundation's Field Level Communications Initiative. To give you a short update before we start with the technical chairman, I like to give you a very short introduction on the OPC Foundation itself. The OPC Foundation status of today has nearly 800 members worldwide, and still our vision is to provide a secure and reliable infrastructure to exchange data completely independent from vendors, from the platform, from the operating system, from languages, and even from domains and markets. And we do this by scaling data from sensor to the enterprise, cloud and back, in a complete end-to-end secure way. For me, it's very important to mention that everything is open. The O from OPC Foundation stands for openness, which means specifications, once they are released, are available to everybody. You don't have to be a paying member. Sample code is available on GitHub as open source, and also the certification labs are open to everybody. You don't have to be a paying member of the OPC Foundation. Obviously, you have to pay the daily fee. So with this, we are really acting as the United Nations for Industrial Automation in the best meaning, which means it is independent. We are providing the neutral ground where all companies can work together and come together to work on standardization. And there's not one single company and not one single country who's able to dominate the OPC Foundation. This is exactly needed to work together on standards. OPC Foundation is providing, together with partners, the promise for industrial interoperability. And this promise is based on 3 pillars, which you see here. On the left side, it's OPC-UA, the robustness and the security and what I mentioned before. In the middle, you have our cooperations with more than 55 partners in the world, and they are defining the semantic for specific devices or machines or services. And the combination of the semantic and the behavior of these machines and the meaning of data and the description together with OPC-UA is the package for the promise of industrial interoperability. Obviously, for this promise, you also need tools and scenarios for validating and certification. And this is what we deliver with the OPC compliance test tool, which has been extended meanwhile to over 1,800 test scripts, not only checking the functionality of an OPC-UA server and an OPC-UA client, but also more and more also testing and validating companion specifications, and we will hear much more on that. Important to know is that we have the complete tool chain to provide from templates, Word templates, which get validated and which get published also in the online reference, which is searchable. And so we try to avoid any double standardizations. Today, we are here to learn what happened with all the work done by the Field Level Communications Initiative, which we have started in November 2018. And the next few slides is just to remember a little bit how it started and give you some impressions. So here you see a picture of the group who made a picture early in the morning of the trade show. Meanwhile, there are many more companies who have joined the steering committee. And I think it's a good momentum to say a very special thank you, because these companies do a lot of extra contribution, not only on budget, but also on human resource, providing all the experts in working groups. Important to realize is that the working groups itself are open to all OPC Foundation members. Remember that everybody has just one vote, every company is treated identical, and so everybody has a right to join all kind of OPC Foundation technical working groups. So if you like to participate, just contact the leaders here and you are invited. It started very impressive with a press conference, with a fully packed room, and we did the promise to extend OPCUA down to the field level and addressing all requirements which is required exactly in the process and in the factory automation world, including deterministic, functional safety, and motion. And obviously, we received a lot of visibility here with a nice picture on the title page of the daily magazine of the trade show. After that, the group immediately started in January 2019. It has been a huge, big effort to get 160 people from 43 companies at that time into the room. It was hosted by Siemens at that time, and the group decided to have Clark Case from Rockwell Automation and Georg Biehler from Siemens as chairman and editors, and they are both also speakers here today. Just a little bit later, in April, the OPC Foundation hired Peter Lutz. Here you see where he gets his first time his new business cards, and he immediately jumped on stage, and from that time he coordinated the field level communications initiative internally in the OPC Foundation, but also in the group and to the outside world. Before we start here, I just want to make sure that everybody has a basic understanding that OPCUA is not a protocol, or let's say it in a different way, it's much more than just a protocol, because it is exactly to standardize data and interfaces and then exchange these data and on different protocols like TCP and UDP and MQTT and so on, from sensor to cloud and back. Second, OPCUA scales from sensor to cloud and back with included built-in by design end-to-end security. Critical important to understand is that when the group field level communications initiative is extending OPCUA down to the field, this does not mean this is a version 2 or an incompatible version of OPCUA. Instead, it's just OPCUA extended. And this is what we learned today by all the speakers. Second, it's critically important that all these extensions are harmonized across process automation and factory automation, because obviously we want to have same handling and interaction as much as possible, what we can do to have an identical behavior and handling of these devices for asset management, power management, firmware updates, configuration, and so on. If you like to learn more about the roadmap of the OPC Foundation, please join our roadmap, which is public in the web. And with this, I like to hand over to Peter Lutz, who is giving you the introduction on the OPC Foundation Field Level Communication Initiative.
Okay, with that, I want to dive into the slides I prepared. So first of all, I want to talk a little bit about the use cases that field level communications is working on and is adding to the existing use cases where OPCUA is used today. So you see here with the numbers 1 to 4, the use cases OPCUA is covering today: IT/OT communication, cloud integration, secure remote access, but also local OT communication. So the field level communications initiative is extending OPC to the field level, and by doing that, it's covering 2 additional use cases. Number 5, the controller-to-controller use case. This is the horizontal integration connecting controllers of different manufacturers. And then number 6, bringing OPC down to the field level to connect controllers with the different types of field devices. And this also includes device-to-device communication. And whatever we do, we certainly keep the complete vertical integration, so there is a direct connectivity across all levels or layers in a factory, from field up to cloud, and vice versa as well. We are also preparing the solution in a way that we can easily integrate upcoming technologies and upcoming trends. This is why we mention here also wireless integration 5G, because this is a very relevant extension to OPC for field level communications to also support wireless connectivity. Now, if we look to the traditional automation pyramid that you are all aware of, having the different layers from field up to cloud, it is clear that if we look at IT, OT, there is still the separation, and OPC today is actually linking IT, OT at least up to the control level. Now, by bringing OPC down to the field level, we extend OPC to really have one consistent connectivity standard that is scaling completely from bottom to up and vice versa. And this is also including deterministic communication, motion, for example, and functional safety, as we will hear later. The formula that is taken by the Field Level Communications Initiative is to combine the existing OPC technology. So it's not changing anything, we are only extending this framework. And we are combining this with different standards out of IEEE. Especially important is time-sensitive networking, because it allows us to have a deterministic communication based on standard Ethernet. And time-sensitive networking is also important because it supports network convergence to allow IT, OT traffic to coexist in a common network infrastructure. Also, very important for us is the advanced physical layer, Ethernet APL, because it brings down Ethernet to the field level in process industry, and so to say, opening the path to bring down OPC as a higher level protocol, and also including the information modeling. What Stefan already mentioned is very important that we have all the major automation vendors with their long time know-how and the expertise to contribute to extend the framework for the different use cases and application areas in factory and process automation. Now, looking at the overall architecture, as I said, field level communications is extending existing OPC technology. This is what you see here in a dark blue color. And we are adding concepts for information modeling, for behaviors, for what we call automation components, including offline configuration, including the connectivity aspect to connect automation components with each other using client-server and pub-sub mechanism. And we are adding the different device models on top that stand for different device types. For example, functional safety devices, motion devices, instruments, and whatever is needed. We also support combining and integrating existing companion specifications. This is the gray box you see on top, So what is already existing can be reused in combination with the different specs coming out of the field level communications initiative. If we look down to the communication, to the network layers, as I mentioned, we are relying our framework on IEEE standards, and also very important for time-sensitive networking is the IEC IEEE 6802 TSN profile, because this standardizes the use of TSN features to have then really cross-vendor and cross-protocol ecosystem for TSN that allows the convergence of IT and OT traffic. And we are defining two communication profiles. We'll hear later further details on that. On the one hand side, supporting UDP over IP, but also supporting a direct layer 2 mapping for more efficient communication. As I said, we prepare for adding additional communication standards in future. Mentioned here is wireless communication over 5G, Wi-Fi 6, Wi-Fi 7. And now what you also see here on the right-hand side is that we take care of conformance testing. So we will provide all the testing and certification tools to allow a high level of compatibility and interoperability across the various vendors. What we cover in today's webinar is everything that is here included in the red box. So you will hear about the base concepts in this middle section, automation components, offline configuration, connecting devices. But you also will hear about functional safety that is, let's say, put on top of these core concepts, and you will understand more how this is then mapped to different communication profiles. If we look a little bit to the organizational structure, you see here 8 working groups that we have set up under the steering committee for field level communications, and the 5 working groups that are now part of the red box: architecture, information model, connecting devices, offline engineering, and safety. They are represented today with the chairman of the different working groups, so that they present the concepts and details on what has been specified so far. Talking a few minutes about roadmap, the steering committee of the initiative has agreed about 1 year ago that the focus is in this, for the first specification version, on the controller to controller use case. And then these concepts are extended to cover also the controller to device and device to device use case. This is what we call C to D and D to D. Now, the working groups have made significant progress over the last weeks, and I would say this is despite COVID-19, which certainly caused also some delay for some of the discussions and work in the groups, because no face-to-face meetings were possible, and we all had to do virtually. And the good thing is that now we have finalized what we call the initial release candidate, RC1, consisting of 4 parts, part 80 to part 83, covering the overview and concepts, covering connecting devices and information model, covering networking aspects, and also covering offline engineering. Why is it so important to have this initial release candidate? Because it is giving us a solid foundation for prototyping needed for the verification of the specifications. At the same time, we are building the test specification out of this initial release candidate, which is finally leading to test cases for the certification tool of OPC Foundation, the CTT. So this is all done in parallel. And finally, all the concepts that are part of these initial specifications are also the foundation for enhancing the concepts to cover, as I said, C2D and D2D in the next step. We have also published about a week ago a 40-page publication. We call it technical paper, which is explaining the technical approach and the basic concepts for OPC UA-based field level communications. And the webinar today is mainly relating to this content, but certainly today we go into more details. But for a general overview, I think this publication is very helpful. And it also talks about the overall vision, the benefits, and the importance of time-sensitive networking and the advanced physical layer. Now coming to the conclusion of my introductional speech, I took again this automation pyramid that you see on the left-hand side. And I would say the big benefit of extending OPC UA to the field level is that we are generating a much more flexible ecosystem where we can support the IT-OT convergence. We are using one consistent standard for communication, but also for the information modeling, including the semantics, really from field to cloud and vice versa. And we are doing this by extending the OPC UA framework for all that is needed for automation, factory automation and process automation, and combining OPC UA with underlying standards like advanced physical layer and time-sensitive network, as well as in future 5G, Wi-Fi 6, Wi-Fi 7. That's it all from my side. My voice has a little recovered. So I'd like to thank you, and we are moving forward with the first technical presentation given by Clark, who is heading our architecture working group.
Excellent. Thank you, Peter. Let me make this bigger. So my name is Clark Case. I'm with Rockwell Automation. I've spent my entire career in industrial automation, starting out with Foxborough Automation, which is now part of Schneider Electric, then working for a small software company that was then acquired by Rockwell Automation, where I have been since then. And during this time, I've worked with customers in just about every sort of industry that the industrial automation serves. And if there has been a consistent theme among all this time, it has been concern about how to make devices from different vendors exchange data. And this has been a consistent theme over the years, as well as across different industries. So back in the beginning, when field buses were first becoming a thing, every different vendor had their own sort of field bus on their own sort of media, talking their own specific sort of protocol, and everyone thought theirs was the best. And for some specific sets of use cases, they were probably right, but there was very little ability to make them interact. And if these devices were to interact, it was in an expensive, slow, and unreliable way. Then over time, as the different industrial automation vendors started moving on to industrial Ethernet as a platform for their field bus devices, things certainly improved. In many cases, devices from different vendors could sit on the same network and happily communicate with each other, as long as what they were trying to talk to was another device from the same vendor. If they wanted to exchange data with each other, often there would still have to be a gateway of some sort between translating the protocols that they spoke with each other so that the information could be understood. And this, of course, also ended up with a solution that was slower and more costly to implement than would absolutely be necessary. And that is more or less what has brought us here today, which with the field level communications initiative, where we are trying to drive the ability for industrial automation devices from different vendors to exchange data in a high performance sort of way with no gateways required. So you get the communications performance between devices from two different vendors that would be on par with the communications they would have with devices from the same vendor. But we aren't, or excuse me, we're trying to address a very wide problem space with FLC. We're not focusing on a single industry. We're not focusing on a single sort of industrial automation device. We're trying to define the problem space very broadly. The sorts of automation devices that we want to address might be as small as a little temperature sensor that broadcasts its measurements, once or twice a second, or they could be in entire room-sized machines that are exchanging data with other room-sized machines on a millisecond or maybe even a shorter time basis. We want to be able to address devices that are built with the latest communication hardware and with very tight timing needs in their networking communications with the latest time-sensitive networking technologies. And we want to be able to address hardware platforms that might not have those capabilities and are deployed on existing network platforms. We want to be able to address scenarios where devices are programmed and configured using software tools from multiple different vendors, but can still be set up to communicate with each other and be set up to communicate with each other when there is significant time and distance and networking barriers between the devices that are being configured, such as the scenario often when different system integrators or different machine builders are providing components of a larger manufacturing system. We recognize the need for and want to address the need for information applications to extract useful information from a wide different variety of automation devices in a consistent way, and to be able to utilize security and safety integrity communications in scenarios where those technologies are necessary as well. And we're not just focusing on controllers talking to devices. We want to address the ability for controllers to talk to other controllers, as is the scenario often when things like process skids are brought into a system and need to communicate with each other, or different complex machines. There are more and more use cases for devices needing to communicate with each other to coordinate their activities amongst different peers without necessarily interaction from the controller in every round trip of that communication. So the controller might provide some command and set point information, and then the devices coordinate their activities between themselves in order to complete some sort of a task. And at the compute layer, they need to be able to access data from controllers, as has always been the case, but more and more the devices also have a rich set of information available that applications at the compute layer can extract and use directly without needing to go through controllers in order to make use of it and get meaning from it. And compute applications need to be able to exchange data with each other in such a way where these different applications understand what that information means and how it is organized and set up. Now, what I've just described, of course, is a very large set of problems to address. So we're not trying to do everything all at once. What we have decided to do first is to focus on controller to controller communications. But we're doing this in such a way where the capabilities that we're setting up, the mechanisms that we're defining, the information models that we're defining are going to be extendable in a very straightforward way to address controller to device and device to device communications. The same approach will be used, the same sorts of models will be used. By focusing first on controller to controller, we can address very significant customer problems, such as the need to bring in, such as in the diagram on the left, bring in skids from one vendor and have them integrate in with some sort of a line controller from a different vendor. This is a problem that our customers face every day. And similarly, scenarios where machines from different vendors might be interacting on a production line and need to exchange data in more of a peer-to-peer fashion, another problem that our customers face each and every day. So by focusing first on controller to controller, we can solve most of the big problems that we will address or that we will encounter as we're going on to controller to device and device to device, and we will give the different vendors of controllers an opportunity to implement this controller to controller capability in what are generally devices with more compute power and that should be more flexible to enable the implementation of these first sets of standards. FLC is being based on a variety of existing technologies. We, of course, don't want to reinvent things that have already been defined. So, of course, we're using OPC UA and we're using several major areas of functionality within OPC UA. We're, of course, using client-server communications. Client-server communications will be used for the establishment of communications between different devices and for making data available from devices up to compute level applications. We'll be utilizing PubSub for the real-time exchange of data between controllers and devices and controllers and other controllers for active control of the system. We'll be using the device information model defined in part 100 for describing the device from an asset point of view. This information will be useful both at the software application level for doing asset management and monitoring the overall state of devices, and it will also be used for checking compatibility of devices when communications are being established to ensure that one device is talking to the other device that it is really expecting. And we'll be utilizing OPC UA safety as defined in part 15, where SIL, safety integrity level rated communications are required. For our offline descriptors, we are going to be utilizing automation ML as defined by IEC. And where network quality of service is required, we will have two major sets of options for devices and applications that require the newest time-sensitive networking capabilities. We'll be utilizing TSN as defined in IEC 60802 in their industrial profile. And in applications and devices where TSN is not needed, we'll be using existing technologies such as PCP and DSCP. Excuse me. And of course, we can't just, list out these technologies and then be done. Otherwise, it wouldn't have taken us, or wouldn't be taking us several years in order to get a standard out. On top of all of these things, we are building a number of new functionalities. The first one I want to talk about are sets of profiles that we will be defining. Traditionally, in an OPC UA specification, profiles are defined in terms of OPC technologies, and that will certainly be the case here. There will be profiles defined for devices that indicate what OPC UA technologies must be supported and the level to which they must be supported. as you would see in any OPC UA profile as defined today. However, we will also be defining some profiles that define networking technology capabilities. And more specifically, we're going to have two profiles that talk about the technologies that are going to be available for doing networking quality of service. There will be a profile A defined that will define capabilities for non-TSN based quality of service. That one, in addition to the non-TSN based quality of service capabilities, will also define the use of the full UDP stack for exchange of data with PubSub. And there will also be a profile B, which will be focused on the use of TSN technologies for real-time control data exchange. And it will focus on the use of so-called raw Ethernet for the exchange of data over PubSub. It will be entirely feasible for the same device to implement both Profile A and Profile B in order to cover as many interoperability scenarios as possible, but it won't be required. And there are a lot of good reasons why a vendor may choose to only implement one profile or another. A vendor for Profile A, a vendor may choose to implement only Profile A if they're trying to utilize existing hardware platforms that don't have the built-in capabilities in silicon on the device necessary to do TSN technologies, and they may be more interested in addressing applications where TSN capabilities aren't needed. A vendor may choose to implement just Profile B if the opposite is the case, if they're interested in focusing on applications where TSN technologies will provide a real differentiator and they don't see the need to take on the cost of implementing Profile A and going through all the testing necessary for Profile A. So again, implementing both will be feasible if for the most interoperability, but it will be possible for devices to be deployed, for devices to be created that only support one profile or the other. They should be able to live on the same network depending on the network architecture, because TSN in general allows for non-TSN based traffic to exist on the network at the same time. But if one device only implements Profile A and the other one only implements Profile B, they will not be able to communicate in that scenario. Excuse me. So in addition to defining profiles, of course, we're doing a lot more than that. We are defining an information model for a consistent way of describing devices and their capabilities. So the information model will give a prospective client for a given device a way to discover what the device is, how it identifies itself, discover its capabilities, so we can find out if it supports Profile A or Profile B or both, find out what its security requirements are, find out what its safety capabilities are, find out what data it knows how to publish, what data it knows how to subscribe to. So it's a very complete information model to let a prospective client really understand what a device knows how to do and how it knows how to do it. Inside that information model, there will be a very important mechanism defined for establishing and managing what we're referring to as connections between devices. Just backing up a second, Paul Hunkar in just a minute will be talking about the information model. And then after that, Georg Biehler will be talking about the connection management mechanism. We're also working on a file format for describing automation devices and their capabilities so that we can support those use cases where different components of the automation system are being worked on in different places and at different times by different people using different tools. This offline descriptor will be the key deliverable in those scenarios for enabling one engineer to know what the capabilities are of a device that exists in some other place. And Emanuel Kolb will be talking about that. And we will also be integrating in the capabilities that we've talked about with OPC safety. And Max will be talking about those capabilities in just a little bit as well. This, of course, isn't the end. As we move forward, we'll be adding in abilities for controller device communications. We already have a team working right now on applying these technologies to motion control. So devices doing high-speed motion will be able to exist in this system as well. We'll be working on information models for specific device types, like servos, like standard drives, like temperature transmitters. In the future, there will be a standard FLC way to represent the data from those sorts of devices. We'll be adding in support for other mechanisms for communications, underlying mechanisms for communications, such as APL, such as 5G, such as whatever other technologies come down the pike. All in all, it's a very exciting time, and I will turn it over to Paul Hunkar to talk about the information model.
Thank you, Clark.
Sure.
Let me show my screen. So hopefully you're seeing a presentation here.
Yes, we do.
All right, then let me continue and we'll go through this. Sorry, I'm rearranging a couple of things on other screens. All right, let me give you a quick introduction to myself. I'm a consultant. I work for Yokogawa. I also work for other people, but in particular, I'm also Director of Certification for the OPC Foundation. I have been working on OPC-related activities for a very long time. I started with OPC work back when I worked for ABB. I've been a consultant for 10 years now, though, primarily working on OPC. I'm an editor of multiple parts of the OPC UA specs, base specs. I'm also chairman or editor on a number of companion specifications. I have been working on different aspects of OPC UA since it started. And I run the certification program for the foundation, which includes all of the OPC UA certification activities. So I have been very involved in OPC UA. So let's continue a little bit. I'm going to talk about the information model aspect of FLC. In particular, I'm going to give you sort of an overview of the information model we have. I'm going to go through the sort of key concepts and key ideas on what we want to do with this information model. And one of the important things to stress is that we wanted to organize and group the existing concepts in OPC UA and apply them to how devices or controllers would use them. So we tried not to invent something new always. We tried to apply things more than anything else. But we'll go through what we've done here. So our top level component is an automation component. It represents the device or the controller. It has in it, or as part of it, an asset model that describes the physical, logical, or the physical, sometimes logical description of the actual assets. We also have a functional model that describes the functionality that this automation component may expose. And we'll spend a little more time later in this presentation describing those two details. Automation component also has some general information specific to the automation component itself. And let's go look at that a little bit. So the first piece we have in it is overall health information for the device. This is based on what the eye describes, so it's a standard place to represent the device health of the automation component. The next piece we have is we've added some capabilities to the automation component that describes the communication capabilities this automation component is supports or can do. So this would be how fast it could publish data, maybe the QoS or the quality of service information that it's capable of supporting. So can it support TSN? Can it support different QoS settings? How fast it can receive data if it's receiving data. And this is the general range of what the device is capable of. You know, maybe this is a slow temperature sensor, so the best it can do ever is publish data every second, which for temperature data is actually quite fast. Usually it doesn't change. Maybe though this is a robotics controller and the device is capable of handling sub-millisecond data rates. So this is all described in the capabilities of the general device. The next piece that the automation component has in it is a bucket of information dealing with offline descriptors. So Emanuel later in our show or in our talks will provide some slides describing how offline engineering works for FLC. This is a set of information that's key for letting devices or letting engineering tools obtain information from the device about what it's currently configured for, what it has in it, what are the options that this device supports. So there's part of this descriptor includes identifier and version information of the descriptor, but it's actually a file too, so someone can download this file and obtain information from the device for how to engineer this device or what this device is capable of doing. We also have some methods that allow systems to establish connections to this device or to close connections. Connections are described later when we talk about functional entities, since they are between two functional entities. So let's go on and describe the functional entities a little bit more and the asset aspects. So in our asset model, I know there's already a lot of asset models out there. What we focused on is describing the asset that's unique to a controller, to a device. In this release, it's primarily been the controller piece, but in the next release, we'll also touch on devices. Assets can be fairly complex. You can have multiple CPUs, you can have power supplies, I/O modules, maybe you have a rack of I/O modules. And the key piece here is that when we're establishing communications between devices, many times it's important to know that the device I'm talking to is the right device and that it has the right features. It hasn't been updated or hasn't been reconfigured, and maybe the I/O rack has been moved. And yet I want to have communications, and the communications I want includes talking to the I/O pieces or to the particular version of a controller that you have. So what we've done is made sure we have an asset model that can describe all the features needed. So the asset model has connection information in it, so I can illustrate what sort of connections I have. I can describe how the device is actually mounted, where it is, what the connector is that it's using. I can have a bunch of actual information about the asset itself, say the serial number, maybe product code information or hardware version information, model information. So this is all information pertinent to this asset. And it's important in some cases to actually have this information available when we're establishing communications. So we have the capability of asset models to actually be nested. So I don't have to have one big model that describes the whole asset. I can describe an asset and describe the fact that the asset has children or submodels as part of it. So I have, a PLC with additional I/O cards. So I can model the I/O cards. Maybe I have a controller that has a capability of communicating through multiple additional I/O cards, or maybe it has a description of the field wiring that's connected to it through I/O racks. So all of it can be described in this model. One of the things we did was we utilized what's already been defined in the OPC DI model. So the DI model describes vendor nameplate, tag nameplate. So these are two interfaces that the latest release of DI spec has added that allows you to describe what your device looks like from a vendor point of view. And it has asset information associated with it from a device point of view. So this is important when we're trying to identify devices and to be able to ascertain that this is the correct device that we're looking for. We've also added our own interface in that provides more FLC specific information, including the version of the FLC model and the version and build numbers and appropriate descriptions for the asset. But the other key point is a method that allows us to validate the asset. What we've provided in FLC includes support for compatibility checking. This is the ability to have an external source call and check if the asset is compatible to what I need. So maybe your asset is version 3 of a product, and maybe in the configuration that was provided that you want to communicate to was defined for version 2. Does that mean that I can't use this module anymore if they've upgraded the version? The hardware itself should be able to answer that question. You say, hey, I'm looking for version 2, are you compatible? Well, the response may very well be, no, I'm not compatible. Or maybe it says, oh, I'm version 3, I'm backward compatible. You can use me for any operation that required version 2. This is something that the vendor has to define when he's creating his application, or sorry, his hardware, so that he knows whether it's backward compatible or not. So one of the key things we did in this model is that we know that there's a lot of existing OPC information models that define their own assets and their own asset types. We didn't want everybody to have to define an FLC asset in their model or in their device. If their device already has the DI interfaces in it, they'd have to extend their model or in parallel define the FLC asset portions, but the existing models can be utilized. So what we're requiring when you look in the automation component in that asset bucket is an object. It doesn't have to be FLC asset type object. It could be any type object, so long as it is exposing the required interfaces. So if I have a robotics object that I've already defined, I can add the FLC asset revision type to it, and then it would be compatible with FLC in the automation component. So let's talk a little bit about the functional entity model. So the asset model described the physical and occasionally logical, because it can include firmware or aspects of the device. The functional entity model describes the functionality that this device exposes. It includes identification properties, again, so I can identify it. It may have configuration data that's supported. It has input data, output data, that's all possible. So a functional entity provides some functionality. This could be as simple as a PID controller, or maybe it's a complex motor, or maybe it's a temperature sensor. Any of these can describe functionality that it has. In addition, we've added diagnostic capabilities, so we want to be able to support providing some diagnostics and how the functionality is working. Optionally, it could also be events that are generated for diagnostic information. The automation or the functional entity also, of course, supports the fact that you've defined a type for it. You can have multiple instances of the same type. So this is where the identification and the input data and other items are key, because it's the same exact logic. It's just two different instances performing two different tasks. Functional entities can also be nested, so I can have a complex functional entity that utilizes other functional entities as part of it. So I can create a nested to any level sort of hierarchical structure of functional entities. And then, of course, functional entities are always related to the asset that they're running on, so that I have a linkage back to the actual asset model that's being used for this particular functional entity. We define functional entities in a generic manner. We expect them to be subtyped. We expect that vendors will create subtypes of these functional entities. What we're providing is the base communications and control aspects, and that the actual data that the functional entity exposes with input data and output data is defined elsewhere. It's either defined in companion specs. FLC is working on some, so the motion control one will define some standard information that's expected in the motion world. Existing companion specs can utilize it, or can add their own information models. So VDMA or the Open Process Automation Forum are all defining information models, and these models can be used as part of the functional entity model. Maybe an automation supplier has a specific model they want to do for what their device is. They're providing a temperature sensor, and they have a model for that temperature sensor. Systems integrators can further extend functional entities, as in they can define their applications as functional entities. And lastly, of course, customers can have solutions too. All of this is valid. We've defined functional entity to use interfaces again. So the key concepts here allow us to add functional entities into existing models. We also have the concept of add-ins supported, which is another way of, it's another OPC UA concept for adding a functionality into an existing model. So our functional entity model can be used in any of a number of manners. So let's look at the functional entity. Of course, we've already talked about the fact that there can be sub-functional entities that can be nested. A functional entity can also adjust the capabilities that were displayed in the automation component. Maybe the automation component says that my device can run from microseconds through seconds for data, and it can support a wide range of QoS functionality. But for this specific functional entity, I may require millisecond communication. You know, that the logic for a robotics controller application that I've written says that it has to run in microseconds. So I can restrict the capabilities that this functional entity requires or can do. I can also provide compatibility checks, of course. So this allows me to check that this is the right functional entity that I want, that it hasn't had updates and changes. To do that, we've added vendor information that's provided as part of the model. I also have application information that's provided, so I can specify what the application is that's currently loaded into this module. I think for the fact that I have a standard function block, and I can configure it in different ways. So this allows me to identify how it's configured. It lets me utilize it and make use of it, right? I have two other key pieces of our information model are the actual connections, which we'll cover last, and then control groups. So let's go a little bit and talk about the control groups. So a control group provides two sort of base functionalities. It provides locking and restricting access. So I can take a control group and lock it, so I can keep anybody else from using this particular control group, so I can lock it to a particular function. But it also allows me to describe the functionality that this functional entity is capable of. So let me maybe explain that a little bit. I can have a motor controller, let's say. I can run the motor controller in two manners. I can have it be torque control or speed control. The controller supports both. Depending on how somebody wants to use it, I can pick one. So I'd have different control groups for that. I have a torque control and a speed control. If someone chooses to use this controller in speed control, I lock it to speed control, and I set it so that that's the only manner of control this controller is using right now. So for a given run or set of applications, I have it in speed control mode. For the process world, maybe the less motor and speed, but maybe this is a PID, a simple proportional integral derivative controller. PIDs support cascade mode and not. So maybe I have two control groups, one that says this is in cascade mode, one that says this is not. So I can lock it to cascade. I can also lock it to PID. The way you use the control groups is really up to the application designer and what they've defined to do. We don't mandate or specify how to do it, but it is capable of a wide range of uses. I can restrict access. I can also block access. So restrict access says that I can lock certain variables or inputs so that only a specific user can make changes to them. Blocking means that I can lock certain things to a fixed setting. So I can take, for example, configuration parameters and lock them to a particular setting. So as long as this communications or this functional entity is in use, I can't make changes to those configuration settings. So, if I'm running a batch process for making a particular blend of gasoline, I may want to lock certain set points in the controller to certain settings and not allow anybody to change it as long as I'm running that particular grade of gasoline that's being made, for example. So our control groups allow us to do some locking. But the key piece that we need, of course, is the actual communications and connection endpoints. So we have a connection endpoint object that's a child of a functional entity. It contains the information about how this logical connection is being defined. Georg will spend quite a bit more time describing this in various levels of details, probably more from the transport section. But the key thing is that the connection endpoint allows me to group input data and or output data, depending on what the connection is, as to what data is being shipped between two functional entities. It allows me to have status information about the connection itself. It also has references to the actual communications that's being used. For this release, it's primarily pub/sub data, but it provides a linkage to the actual data that's being communicated and how it's being communicated. You can have multiple functional or multiple connections as part of a single functional entity. So a functional entity may have connections to 2 or 3 or some number of other functional entities. It may only have one connection. Connections can be bidirectional or unidirectional. And again, Georg will spend quite a bit more time explaining these connections. But the key thing is that we do have a model that lets you see what the connections are and to handle the connections. The locks that we talked about are usually tied to these connections, so that if I set up a configuration and locked it to a particular setting, it's active as long as this connection is active. So let's go on and talk a little bit more about other general information items. I have aggregates, or I have a whole bunch of reference types that define and provide semantic meaning to the information model. I have data types that allow me to show structured data. Of course, I have structures and enumerations that are all part of the information model, all that let us look at data. I have the last piece that we haven't talked about, which is something that Georg in the presentation following me will continue on, is connection manager. So we've described an automation component, that's the device, but I also have a piece that allows me to create connections dynamically and how to establish these connections. This is called a connection manager. That's part of the information model. Not every device has to have a connection manager. Matter of fact, you could have a connection manager that's not part of any automation component. So it's a standalone item. It could also be part of every controller if you want. It depends on how you want to establish the connections and how you want to establish communications. So with that, that's sort of the end of my set of presentations. I think I ran over a minute or two, but let's continue on with Peter, who will, or sorry, with Georg, who will describe the connection manager and the actual connection logic.
Okay, thank you, Paul. So we pass over to Georg, who is chairing our Connecting Devices Working Group. So Georg, you should be able to share your screen now.
Yes. Hopefully I did it right this time. So,
Yes, looks good.
Good. My name is Georg Biehler. I'm with Siemens AG, and I'm chairing Connecting Devices Working Group, as you see here. I'm at Siemens for about 33 years now, so it's quite a long time. And since I would say 28 years, I'm doing industrial communication and industrial automation communications. At the moment, before joining the FLC staff here or the FLC working groups, I was editor of the Profinet specification, and now I'm since 2 years actually from Siemens at the FLC working groups to help doing the specifications. Second. Come on. Yeah, here's the content. What I want to say, what I want to show you today is one thing is what are the logical connections, which already Paul told us some parts of that one. How do we map them to OPC communication models? And how are logical connections between automation components established? And last but not least, what is that connection manager and connection state machine? So how is the establishment of connection? How is that done in an FLC, in an automation component? First, what are logical connections? So what we heard already is a functional entity actually has some input data, some output data, some properties, some diagnostic data. It has processing inside and configuration data. That was already told you by Paul just in the prior to my talk here. And he also introduced some methods around that functional entity which are provided. So functional entities provide that input data or like to get input data from somewhere, process it, like to produce output data. And how do we get input data from outside and how do we provide the output data to somebody else? That is done using a logical connection. So logical connection at the first part is data exchange. It's data exchange for example, controlling things or monitoring purposes. So what data is exchanged? Actually, our initiative doesn't care. Could be anything. It could be a Boolean value. It could be whatever string or something like that. It could be any data type, including structured data types. But the other thing of a logical connection is between devices or between automation components, being a controller or being a device, if you look into the future. Establishing a logical connection, so if we set up the connection endpoint here, we've seen that already in Paul's slide just a moment ago. If we set up that connection endpoint, a logical connection will have additional things which they are including into the establishment process. That is, one thing is verifying whether that functional entity is the one we expect it to be. Is it compatible? Is the automation component compatible? For example, firmware version, hardware version could be checked here. For the functional entity, all that identity information which Paul showed you a moment ago is checked. So if we got over this hurdle, we check whether the output data we like to get from that functional entity and the input data we like to get from that functional entity is valid, is of the right data type, for example. We will establish the ownership, that control group Paul talked about a little bit, which is actually, for example, preventing that somebody else is writing the same input data, which is part of that logical connection. Or somebody changes the measurement value of an output data, for example, from degrees Celsius to degrees Fahrenheit, which could make some trouble for the other one hearing that information. We also have, when setting up the connection, configuration of the data, configuration of application parameters, like the measurement unit I talked just a moment ago. And in addition, that is actually done for, is it the right thing? And we set it up exactly, and we prevent that things are changed while the connection is running. What we also do is we have to set up the data exchange itself. So we set up the communication model, just two slides more. I explain what the communication model is. We set up, for example, the exchange rate, be it microseconds or be it seconds. And we set up also the quality of service to use, be it best effort or up to deadline, which is provided, for example, by TSM. We do all this check on this connection endpoint and also on this connection endpoint. And last but not least, we enable the data exchange so that the data is flowing between the functional entities. Data is flowing between the functional entities could have three different types we provide for a connection. One is a bidirectional connection, which is actually both functional entities exchange data in both directions. So output data is transported over to that functional entity, is received as input data, it's processed somehow, output data is produced, and is transported to the first functional entity. Unidirectional is one thing what you know typically, or what you know probably from PubSub. Somebody provides or publishes data, somebody receives data. No back connection. This one is providing data, this one is receiving data, period. We introduced a third connection type, which says it's unidirectional with heartbeat. What does that mean? It's actually the same like the scenario unidirectional, data flow in one direction, but you get back a message without the data content. So there is no application data flowing back, but this functional entity indicates by sort of a heartbeat, but it's still living. With that, the functional entity can then use means to sort of, if it doesn't get any more a heartbeat, to stop, for example, publishing the data to save bandwidth on the cable, for example. Mapping to OPC UA communication model. I think Clark already said something about that, but we will base on existing OPC UA communication models, which are defined in the base parts of OPC UA, which are already provided, which is just for one thing, OPC UA PubSub, which is defined in part 14, and also OPC UA client server for example, for connections which don't need that speed what PubSub gives you. Client server will be provided after the first release, but we will consider that our establishment of connection will work also for establishing client server connections. And we will utilize also the features of those OPC UA communication models, which are already provided, like optimization of network traffic. So aggregate, for example, data into a network message to save bandwidth on the network, or use of multicast messages where appropriate, and also use of quality of service, which are provided by the base layers. PubSub, and actually Clark told you about that already. We have five different quality of services. One is best effort, which is actually pushing out a UDP PubSub message, for example. The second one, priority. Give that UDP message an IP priority or a PCP priority, a priority in the Ethernet header, in the layer 2 header. And we have 3 quality of service types which are implemented using TSN features. One is, I guarantee a specific bandwidth. That means the publisher can be sure that his packet is, or his frame is transmitted to the subscribers, and it will not be dropped due to congestion scenarios on the network. Max latency and deadline will ensure that the frame is actually delivered in a specific amount of time, and deadline especially is usable for example, for isochronous scenarios. So if you want to, for example, synchronize multiple drives to actually to do something. So example how we map logical connections, which are actually between 2 functional entities. We map them to PubSub. We could, for example, if we have 2 functional entities, A1 and B1 communicating on 2 automation components, or A2 and B2 communicating on the same 2 automation components, we could aggregate those 2 logical connections into one PubSub network message. The PubSub network message is built by creating a writer group on automation component A, for example, for the data flowing from A to B. And inside that writer group, it refers to 2 dataset writer, one containing the information from functional entity A1, and the second one containing the data from functional entity A2. And this will go over the network as one network messages containing the 2 dataset messages here, containing the data from 2 functional entities. And we can do the same in the back directions. In the specification, there are a bunch of more samples like packing of data, like using multicast. But due to the time we have, and due to the short time I have for presenting all that, I refer to read that in the packets if you get the packets in product. The connection status, we also saw that on the slide from Paul. The connection status is actually one element from the connection endpoint itself. The connection status is derived from the communication model. So if we look, for example, for this connection endpoint, the status is combined from the dataset reader A1 and the dataset writer A1. Oh, it should be DSW here. Okay. Wonderful. Okay. The connection status is derived such as we have a status which is called initial. The connection is in progress of being established. That means, for example, verification is done, but not yet. The control group is not locked yet for establishing the ownership. Somewhere in between of setting up a connection. Ready means the connection is set up completely, but it's not enabled yet. So enabling is the last step of setting up a connection or establishing a connection. If we now enable the connection, both the dataset reader and the dataset writer will be enabled. And we go into the state pre-operational. Pre-operational is sort of an intermediate state, which is it's close to operational, but not yet ready. For example, in this state we will wait on a TSN stream to be established if we use TSN, if we use a quality of service which relies TSN as being there. Or pre-operational could be the dataset writer is already producing data, but we didn't get data back like a heartbeat, or we didn't get data back from a dataset reader. Now, if the connection is working, we go into state operational. And if something happens like a data reception for a configured timeout is that we didn't get any data for a configured timeout, we go into state error. In the state error, we defined a cleanup timer, which could be something between a small amount of time and infinite, which takes care if the counter expired and we stayed too long in error. Let's say we set that up for 10 seconds or so. The connection will be cleaned up. But it could also set it to infinite. That means the connection stays around even if it is an error. So how do we set up the connection? Especially, and that is actually the role of a connection manager in going through the connection configuration workflow. So consider that we have two engineers, one engineer here and a second engineer here. And both are using controllers or PLCs, name it as you want, for some purpose. This could be, for example, the controller for a machine, but it could also be a controller for some process automation stuff. What you have, as of today, your task is typically you sit as this engineer, you sit before your engineering tool, which is dedicated to fill up or to engineer exactly that PLC. And that engineering tool comes from the same vendor as that PLC. Let's name it vendor A. Vendor A produced this PLC. We have the engineering tool for vendor A. And vendor B's PLC, vendor B's engineering tool, and engineer B is sitting here. So let's consider both PLCs should at some point of time talk to each other. How do we do that? So one thing is that the engineer A is using the engineering tool as of today to write a user program to write the hardware configuration of the PLC. But since we want to provide that PLC, or we want to make that PLC be an automation component, be an FLC PLC or FLC capable PLC, here's also to define a functional entity. That is that thing, what we've seen on Paul's slide and maybe also in slides before. We have to provide sort of the interface to the outside world with input data, configuring data, output data, and also with the capabilities. I'm capable communicating with a bunch of publication intervals and maybe with the quality of service, best effort, and priority. So at some point of time, engineer A will download this project into PLC-A. So the user program hardware configuration as of today will sort of be put into the PLC-A by using vendor A's specific download protocol. And also the functional entity will now be established, and the automation component will be established in the PLC-A's OPC server. So automation component functional entity is sitting around here. And automation component provides capabilities, functional entity, and maybe also the network stack. So, but now how to inform engineer B? Oh, I'm providing that bunch of output data, that bunch of input data. So write your program and your functional entity so that we are able to communicate. For this, he will export a configuration descriptor, and Emanuel, just following my talk, will describe that in detail what a configuration descriptor is. But for now, it's describing actually the functional entity interface, what you've seen here. Yeah? It's describing what input data is provided, what output data is provided. So PLC-B engineering tool or engineer B imports it into PLC-B's engineering tool and writes a usual program, writes his functional entity or maybe multiple functional entities for communication with other PLCs, and writes something called connection configuration set. We will look at that in detail in just a moment, and we'll download that again into his PLC. So the user program is installed, the functional entity is installed, and the connection configuration set is downloaded in that thing called Connection Manager. So what is the connection configuration set? First thing, connection configuration set is a set of connections. Remember some slides ago, I've shown you a sample with two logical connections between two PLCs. So the connection configuration set would in this case contain the two logical connections. And per connection, you have two endpoints. And per connection endpoint, you have all that information, what we need to check, for example, verification parameters, what we need to apply, application configuration parameters, and communication parameters also. And also we have the address of the automation component and functional entity of that logical connection partner. And remember, for each logical connection, you have this set information twice for the left and for the right endpoint. And also the connection information indicates modifiable parts in that connection information and the predetermined range. Why do we need that? Think about our engineer A and engineer B are sitting in their department at some machine builder's factory or whatever. And we deliver the machines, PLC A, including the machine behind it, and the PLC vendor B or engineer B delivers his PLC to some customer. And on the customer side, we have to talk to each other. At the customer side, we will get a name and we will get an IP address. So that is bootstrapping, which we will cover also at some point of time in our specification, how to assign names, IP addresses, etc., to the automation components. And for this, we need to, since the connection configuration set also contains that address, we need to have the possibility to change that address at the system integration phase. And for this, the connection manager exposes the connection configuration set in his information, in the information model beyond the connection manager or sitting underneath the connection manager. And the system integrator, this orange guy here, is now able to modify parts of the connection configuration set within the predetermined bounds, which actually engineer B decided. I want this information to be changeable. For example, the name and the IP address, maybe also allowing the publication interval to be tweaked or whatever. So he is able to, the engineer B is able to determine in what bounds the generic OPC UA client is able to change. Now, we've set up everything, still no data is exchanged. So how is that working now? The connection manager is actually exposing a process method in his address space at the connection configuration set. And this method could be now called from external or could be triggered or processed internally by the PLCB. Maybe PLCB knows that I have to establish the connection configuration set with two things, and this one is not established. Now it's a good time to establish it. Now what happens? The connection manager does all the checking, verifying that the functional entity has the right identity, is compatible and logs it, applies configuration parameters to the functional entity, etc., etc. And then, last but not least, creates a connection endpoint in the information model underneath the functional entity. This connection endpoint is actually the representation of the connection inside the automation component. So you see there is an active connection. Then the connection manager will create the communication model. That means he's creating a subscriber that is a pub/sub connection, a dataset reader group, dataset reader, and so on, with the quality of service. And he creates a publisher, writer group, dataset writer. This side is sort of set up. And now he goes over and does the same thing at PLCA. So notice we have here a remote call, and this is actually a local call. Maybe done in a vendor-specific way, because it's inside PLCP, but it's this call, and this call is doing the same things in a sequence. So a connection endpoint is created here, publisher and subscriber are set up. If the quality of service here is best effort or priority, it will be enabled, or both will be enabled. And if the quality of service is best effort or priority, data is flowing across the wire. If we have a TSN related quality of services, we need to establish a TSN, using the TSN control layer, we need to establish a TSN stream, and then the data is flowing if the TSN stream is established. Yep. And the same thing from a connection manager. So it's built in a way where it could be part of a PLC, it could be part of a device, but it could also be part of an external server. So it does the same thing here. The connection configuration set we'll call establish connection on PCA and PCP. Okay, that's what I wanted to present you today in my talk. And I will hand over to Peter, back to Peter, so that he hands over to Emanuel.
Yes, thank you very much, Georg.
You're welcome.
So next speaker is Emanuel Kolb, who is chairing our offline engineering working group.
You hear me?
Floor is yours.
Okay, so I'm going to presentation mode. So my name is Emanuel Kolb. I'm with ABB. I'm working for field device integration, networking, and engineering for the process automation division. And in standardization, my standardization activities are on the one hand side participating in the FDI, field device integration group. On the other hand, since the beginning, I'm also part of the FLC, Field Level Communication Initiative, and I'm the chair of the Offline Engineering Working Group. Let's go to the next slide. So this is a little bit about the content. So I would like to introduce you to the work we did in field level communication offline engineering. So starting a little bit with some life cycle and the context of offline engineering, and next coming to the main concept that we were working on. It's about the field level communication descriptor idea. Further elaborating this in the two flavors we are currently have more detailed concepts also ready, giving you some technology details, showing an example, presenting you an example, and last but not least, having one slide connecting back to Paul Hunkar's presentation, that offline engineering concepts are also available at runtime in our architecture. So to start with everything, when field level communication initiative was started, it became soon clear that you cannot expect communication interoperability if you don't deal also with the engineering process. So especially the collaboration between engineers. So therefore, the offline engineering group was established to analyze this and to create some results. When we started that and had our sessions, it became also clear that you cannot standardize an engineering process. The vendors have their own way of doing things. The markets have a different approach. But there's one area where a standardization makes sense, and this is where data is shared in the engineering process between engineers. So that is a little bit more explained here. So what you see here is a kind of overall workflow about engineering process with the stakeholders for a plant. So starting from device vendors selling devices, controllers, going to machines, kit builders that assemble things together and reselling it to installations, to plant owners, to factory locations. And what you see on the right side is what is called the value chain. This is, of course, where the components get delivered from one location to the other location, then gets assembled together and finally gets commissioned in the plant. But it's important to know that this hardware sharing, this hardware provisioning, this supply chain is not the only supply chain that exists. So this is maybe the most visible one. But already before, there is a sharing of things between the actors. But this is not a sharing of tangible assets. It's non-tangible assets. It's just data. And so it's a little bit hidden in the overall view. And this is exactly where engineers sharing data about their components before the components get delivered to the site, so that the receiver can already start planning and designing the machine and has not to wait until the hardware is coming. And this is exactly the way, the area where we started working, and we had a closer look what kind of data is shared between engineers during their design process. So if you look into, this is also a very rough and typical slide on actors and data shared, but as you've seen before, we have component vendors on the one hand side, we have skid and machine builders on the right side, and on the bottom, the system integrator. And you see a little bit the kind of data that gets shared during engineering. Of course, this workflow is a little bit focused on the controller use case, but in the next phase, we will also extend it to, and it's not a big issue to extend it to other design processes. So what a component vendor is sharing to a skid machine builder is, of course, the information on the structure of the component, of the controller. So it's basically the asset. I think the asset information model Paul Hunkar presented very detailed. And part of the assets are the capabilities of the components, the identification, constraints that the asset have, power limits, and so on. All this stuff is part of this first set of data a machine skid builder is using for assembling the machine. Of course, but there's also data that is not that it's not part of a formal information model, at least not normally. So there could be documents also, manuals, drawings, pictures that is can be useful for understanding how to use a component. So there are two types of data. I would say there are more formal data that is part of the information model of the machine, also if it's running in the online phase. But there's also a kind of attachment documentation that helps to understand the engineering process better. In the next arrow here, we have another use case is where the machine skid builder is delivering his design to a system integrator so that he can already plan the factory without having the hardware available that comes later. And in this case, for the controller use case, a machine control engineer will add to the controller the functionality. So the application programs will be written, the functional entity structure will be created, which also exposes the input-output variable and the configuration variables that are being used to configure the functional entity. Part of that is, of course, also settings on communication that are needed for setting up client-server and pub-sub communication, like communication rates, periodic ones, quality of service, timeouts. I think Georg, in his presentation, showed you already, give you a little bit insight into the data that needs to be configured in order to that two machines can start up a communication. Last but not least, there's also a use case that machine skid builders are exchanging their configuration and asset data with each other. This is a use case Georg presented also where a PLC-A engineer was sharing data with PLC-B engineer in order to that each others know about what kind of data can be expected, what are the rates and the conditions, constraints for the communication, so that PLC-B can configure things in the right way. Yeah. So this is a little bit on this data that gets shared. Then I would say the next question, of course, is how this data gets handled. So are you sending each document in one email, or are you putting this together? Normally what people do, they, of course, they create zip files out of these things and sending it over. But a zip file, of course, is creating one file out of multiple files, but it does not have an internal structure. So nobody tells you what is a starting document you have to open. Are there any relationships between these things present? And also, there's also a kind of security issue here because there is no digital signature for zip files. So there is a kind of mock-up security with a password, but this is, I would say, not the right security approach here. So there is some improvement that is needed here. And in order to tackle that, the FLC offline engineering group developed a concept that is called descriptor. So as a short name, descriptor. So basically, it's also a container. It's one file, but this file is containing all the stuff that gets shared between the engineers and put it together in one asset. And we have additional things here also that, for example, a digital signature is part of this concept. In the next slide, I show you the details about this descriptor. So we developed this concept as a kind of general descriptor idea. However, what you see here is already some flavors of a descriptor. So component vendors will share their product descriptions with machine and skid builders or even the system integrators. So we call this kind of descriptor a product descriptor, and machine skid builders will share data among each other or with the system integrator, and we call this descriptor configuration descriptor. The main concept is the same, but it can contain different kind of data, as you see here, either the red stuff or the green data, the green things here. So looking a little bit closer what a descriptor is in our concept. So what I have said already, this is basically a file, a container file. It has also, it uses a zip compression technique but it has additional structure. The additional structure, for example, has some metadata on that this descriptor has an identifier, it has version information, it has a kind of small table of contents that leads you into the content. So there's also a start document that you open first in order to navigate through the rest of the container. Then there is a section about modeling. So basically, this is the information model part, showing the structure of the information model of the later online device, and having the ability then to set here the parameters for the configuration. These modeling files are written in Automation ML. I come in the next slide, or in the slide later, on the technology a little bit more. As a next, you see a section called attachment. This is all things that are non-modeling files. This is supplementary information that that helps support the humans doing the engineering and understanding the functionality and the setup, the structure of the component. So this could be a drawing, this could be a manual, there could be, but even also firmware things that belongs to this component and maybe even gets later downloaded if there's a firmware update. There's another section called inputs, and this allows you to also put descriptors in a descriptor. And when I show you the configuration descriptor, it will be more clearer why this is useful, because that helps you also to track, to include information that was made by others into the descriptor, and not, I would say, and putting the whole descriptor in and not tearing it off and selecting parts out of that. Finally, we have a signature concept here. Usually there's only one signature, but there could be more. But usually the creator of the descriptor is then digital signing it. We will add also, the person will add the certificate to that. The certificate chain will be included. So a receiver of this information, he can check who has created it, and if he can follow up the trust chain, and if both have the same trust anchor, the descriptor information can be trusted by the receiver. So how does it look like for the product descriptor? For the product descriptor, this will be containing basically the asset structure of a controller. It will have the identification information. It will have capabilities of the asset, constraints of the asset. It will be, of course, all the references between the assets that Paul Hunkar has shown in his presentation. The attachments will, of course, have everything, could have everything that a vendor thinks is useful for an engineer to understand the functionality and the purpose of the component. And of course, there will be a vendor's signature of the component vendor. So so you will get a descriptor from your component vendor, and of course you have to decide whether to trust or not to trust it. A configuration descriptor is similar to that, but of course it has a focus on different kind of modeling data. So for a controller, there will be the functional entities, structure of the functional entities included, which describe the interfaces to the applications that the controller is running. So part of that are the input and output variables, the capabilities for publishing and subscribing, the quality of service, rates and timeouts. And this can be also, it can be fixed values, but this can be also ranges, so that configuration engineer is saying this information can come with different periodic rates. And finally, in the system integration rate phase, the system integrator has to select a number that finally fixes the communication. You see also some drawing can be included, but what's maybe a highlight here, that in order to make this information complete and also to let's track back what was the asset structure here, what are the, where is Emanuel? So there's also the possibility to include the product descriptor with the signature of the component vendor as part of the configuration descriptor. Yes, and finally, there is also a second signature here. So this is a signature of the machine's kit builder. This is a required thing. We said this is mandatory to have a signature for every descriptor. We don't want to go without security for this concept. Okay, let's move on and look a little bit on the technology used. So as I said, there is a zip container compression for the files in a descriptor, and there is a standard for that that is called Open Packaging Conventions, which was created some time ago by Microsoft, and it's still in active use in the Word and Excel in the Office documents. So every Office document is also a container, but it does not, it has of course its own file ending. We also use a specific file ending for the descriptor. The ending is AMLX because this was also defined, there was also packaging defined by Automation ML based on open packaging conventions. So we're just reusing this concept here. In addition to have the capability to pack files together, the Open Packaging Convention standard also has the ability to define relationships between the content. So these are special files in the container that define relationships. And so this makes it possible to for example, to define a table of contents with this relationship, to get some navigation into the content from a start document. And so this helps to better understand the structure. And Open Packaging Convention also has defined a dictionary signature, and we just are using this whole concept and saying this is now the standard for the field level communication descriptor. So this is the one technology used for the packaging, and there is another technology that we are applying for the modeling. As I have told you, the modeling information in the descriptor is coming from the information model, so it's resembling the information model. It's showing part of the information model that where the structure was shown by Paul Hunkar, and but we have not decided to take node-set files for this purpose. We have looked a little bit around, and we have seen that in other standardizations, Automation ML is used, and this is a quite valid and well-proven XML-based format for plant engineering. So what we are defining is that the modeling information in the descriptor should be based on Automation ML. And this allows also for some simplifications in the model. And also we can use also additional features that are not available in the node-set format. So we could, for example, define metadata and external references, also deep links into other documents via this. In addition, there is some future use case we have to think a little bit more, is that Automation ML has also integration capabilities for integrating other information models into its space. So when FLC will evolve further, it could be that we have some links to PLC Open or to young netconf information for defining, for example, configuration for embedded switches. So these are the two technologies we are using. And then the next, I would like to show you one example, but this looks a little bit technical. But anyhow, I will just jump into that. This is an automation ML model of an automation component. So what you see here on the left-hand view, on the left view here, this is an automation component. It's just a vanilla one that is structured as you have seen in the presentation from Paul Hunkar. So this is somehow very close, resembling the OPC UA based model. And in our work, we paid a lot of attention that we make it possible to have the object types, variable types of OPC UA also available in AML. And for that, there is, or part of our work, a special library that we will provide with a specification. This is called FLC AML library, or FLC library for short. This library will contain for each type from the FLC space corresponding type in AML. So you even see that there's the same name. And so with that, you have some easy or some jump up start possibility to come to AML modeling of automation components. So this is one big advantage that we will provide. The other, I have to say, of course, control engineers will probably not work with these kind of simple user interfaces. They would like to work with their control engineering environment. So this is out of our scope that we make mandatory requirements on the engineering tools that are all over, how they should look like. But we would expect that if FLC comes to the market, that engineering tool vendors will provide the capability to import the descriptor to present the structure of a descriptor in a I would say, a nice way, and to allow editing the descriptor data and also in the end allow to export a descriptor for sharing to other engineers. That is a little bit here described in this slide. So on the one hand side, we'll be providing this AML library for the FLC concepts. And on the other hand, which is just an expectation, so we would expect that engineering tools will be able to work with a descriptor, and also in addition that component vendors will of course make their offline data of a component available as a descriptor for their product, so that it can be used in the offline engineering process. Okay, now I would come to my last slide, and this is just about coming back a little bit to the presentation from Paul Hunkar. The descriptor is, of course, clearly an offline engineering concept, but there is a kind of, it's also available at runtime. It can be available at runtime, because in the information model, there is a section that where it is able to access the descriptor as a file. So we envision that the product descriptor can be stored here already by the component vendor when it delivers the component to the customer, that in the startup of the OPC UA server, this product descriptor will be already part of that. So this makes it possible that if an engineer later comes to a plant, gets to a controller, wants to know what is the data, what is the structure of the whole thing, that he can just download the offline descriptor from the controller and browse through the structure and start its engineering tool with this data filled. And so he has a better I would say, start up for talking to the online device, then browsing the space and getting the information piece by piece by using OPC UA client server calls. This stuff is optional, so of course the product descriptor of course is a file. It needs some memory, so for embedded controllers for very small devices, it would be probably not possible to store a product descriptor there. For that, there are other means. For example, the offline descriptor identifier is a unique identifier for finding the descriptor. So either this could be a uniform resource location in URL that you just put into your web browser and you can find it on the product vendor's website, or it's a kind of URI that you have to enter in a search form, and then it will lead you to the product descriptor. So that's the idea behind these offline descriptor identifier, the version, and the descriptor file. With that, I'm finished for now.
Yeah, thank you, Emanuel, for the introduction of offline engineering and the descriptor concept. We go then to the next presentation given by Max Walter, who is chairing our safety working group. So, yes.
Yes, good evening, everybody. Good morning, everybody. Thank you for having me here and giving me the opportunity to present here OPC UA Part 15, Safety. My name is Max Walter. I work for Siemens, and I have the honor to be the chair of the Safety Working Group. So this is the content of my presentation. I will first give an introduction about what is functional safety for communication, and then I will show you the key features and a short technology overview on OPC UA safety. And of course, I will talk about the relationship to FLC, so what we have seen here in the other talks today. And finally, I would also give you some information on the current status of the specification project and our future timelines, so what we are planning to do. So here I have put together 4 case studies from different domain: manufacturing, process industry, energy, and transport. And what these case studies have in common is that they have safety functions. Yeah? So they are all safety critical. For example, the wind turbine, if it moves too fast, if the wind is blowing too strong, this has to be detected, and then brakes have to be enabled to stop the movement of the turbine, because otherwise this would be dangerous. If it is running too fast, then the whole system could break and things would be flying around, and this would be very dangerous. And of course, also in manufacturing, so we want to avoid that somebody puts his hand in the wrong place, and if that happens, this has to be detected and this system has to be stopped. If we talk about process industry, then we often want to monitor pressures or temperatures, and if they get too high, then we have to do something. And in the train example, with the fast train you are seeing here, then clearly we want to make sure that all doors are closed before the train is leaving the platform. So otherwise, the train has to wait until the doors are closed. And to realize these safety functions, you need safety components. You need some safe sensors, you need safe controllers, and you need safe actuators such as brakes and things like that. And this alone is not enough, but these components have to communicate with each other. So you have to be able to send the sensor values to the controllers and then the control signals to the actuators. And if you do that, you have to make sure that errors are detected during communications, and then the receiver of the telegrams is reacting in a safe way. So, and this is described in detail in the relevant standard, the IEC 61784-3. So this is from the field bus series of standard, but it's also applied in a more general way for all kind of safety communication nowadays. And this standard lists the requirements on safe communication. So in particular, it says you have to implement measures to detect any kind of transmission errors. And this has to be done in the receiver. And then if the receiver detects such an error, it has to react appropriately. This typically means that the receiver is switching into a safe state. So if the receiver is a brake system, so that safe state typically would be enable the brakes, stop the system. Or then if it's a circuit breaker, then typically this would mean open the circuit or something like that. The standard also lets you know what are the classes of transmission errors you have to take into account. For example, you have to be able to deal with messages which are completely lost, which just do not arrive at the receiver at all, or you have to deal with messages where the content has been corrupted by a bit flip or by some other problems, and even more, you have to be able to detect misaddressed telegrams, telegrams which were sent to the wrong receiver, or telegrams which are everything is okay, but they are simply too late. So they took too much time. And in a real-time system, this can be dangerous. And the standard not only demands that you deal with these kind of errors, but you also have to show that the residual error probability, so that is the probability that an error occurs which is not detected, is acceptably low. You have to show that the probability is very low. And you have to give two probabilities, the so-called probability of failure per hour and the probability of failure on demand. And you have to quantify. So, and this is what we have achieved in the OPC UA safety. So we have designed the protocol in such a way that it fulfills the requirements of 61784-3. And we have also a letter of conformity is now available from a certifier, a so-called notified body. In this case, it's TUV in Germany here. They have certified that OPC UA safety is indeed conform with this international standard. By the way, OPC UA safety has been developed in a joint working group between the OPC Foundation and Profibus and Profinet International. And let me take the opportunity here to thank all the members of this working group. We are people from about 30 well-known companies in the area of functional safety and automation in general. And I'm very happy to work with such a team of experts here. So what exactly is the scope now of OPC UA Part 15 safety? So when we began in 2018, so our original scope was to establish functional safety for communication between controllers of different vendors. So, and later on, now also the field level communication initiative has decided to use OPC UA Part 15 safety within the context of the field level communication. And that means we extended our scope also to the field level. So what does it mean? Let me come back to the examples. If we see these wind turbines, then we would assume that each wind turbine is represented by at least one controller. So each wind turbine has its own controller, and then we have some sensors within the turbine, let's say wind sensors, rotation speed, and so on. And we also have actuators such as the electric drives and the brake system. And then we have this internal communication within the wind turbine, which must be safe. So to control if the wind is too high, we activate the brakes and so on. But we may also have communication between the individual wind turbines. It may happen that within a wind park you have wind turbines from different vendors, and that would also probably mean that the controllers inside the wind turbines are from different vendors. And now you can, with using OPC UA safety, you can now communicate between the wind turbines, even if they are from different vendors. What would be an application here? So it would be possible, for example, if one wind turbine detects a gust of wind, a very high wind speed, then it could already warn the other wind turbines that the wind is likely to increase also a little bit more in the distance. So what are the key features of OPC UA safety? So first of all, of course, it is using OPC UA services such as client server or hub sub with and without TSN. So you can use that. The basic building block of OPC UA safety is a unidirectional communication link. But of course, if you instantiate multiple of these links, you can also set up bidirectional or multicast communication patterns. Within each communication link, you can arbitrarily structure the user data. So the structure of the user data depends, of course, on the application. So for example, you could put in some Boolean values and some integers and so on. And the supported data length are from 1 to 1,500 bytes. If we talk about more than 2 nodes, it's also possible to set up arbitrary network topologies such as lines, trees, star, ring, and so on. A quite unique feature of OPC UA safety when compared to existing safety protocols is its ability to dynamically establish safety connections during runtime. So this is, for example, important if we think about automated guided vehicles or autonomous mobile robots, which are moving within a factory and moving from one machine to another machine, and depending on where they are located, they maybe want to establish a safe connection with that machine they are operating at. And this is possible with OPC UA safety, that you are using one interface to communicate with different machines at different times. And of course, this may also be useful if we talk about modular reconfigurable machines and things like that. So this is an interesting feature which I think will be very useful in the future. So with respect to non-safety regular network participants, often there's the question, is it possible also, or what requirements are there on these regular network participants? Isn't there a risk that these network participants disturb the safety communication and make the whole safety system unsafe by such a way? Because regular network participants and safety participants are using the same network, the same Ethernet cable. And the answer is, from a safety point of view, there are no requirements, because OPC UA safety is able to detect such disturbances. So it will be noticed that there is a problem, and the receivers are going into safe state. Of course, from an availability point of view, that might be a problem, because then all your safety components go into a safe state and your system is no longer operating. But from a safety point of view, there is here no requirement. Also, synchronized clocks are not needed to implement such a OPC UA safety. So this is, I think, a good feature. And the number of network components, I'm talking now about switches, routers, and things like that, and terminals, so that are the participants in the network. And also the data rate is not limited, at least from an OPC UA safety point of view. Of course, in practice, all these numbers are limited, but OPC UA safety itself does not has here some requirements that would limit the data rate or the number of network components and terminals. So to explain a little bit how it works, I have tried to put the essence of OPC UA safety on a single slide. So what you can see here is the so-called safety provider at the left-hand side and the safety consumer on the right-hand side. So this is a sketch of a sequence diagram, as you can see here. And what you can see is this kind of ping pong requests. Yeah? So the safety consumer at first sends a request SPDU, so safety protocol data unit, to the safety provider, and then the provider replies with the response SPDU. And of course, in practice, this is repeated infinitely oftentimes, so we have some cyclic behavior here, and now you can see one cycle of this cyclic behavior. And what is important here are now the whole yellow fields I've shown here within the response SPDU. So the response SPDU, of course, first of all, it contains the safety application data. So this is the data the consumer wanted. This is the reason why the consumer sent the request to the safety provider. And in addition to the safety data, now there are multiple fields which contain information which allows the consumer to check whether the transmission of this data here was correct. So for instance, the first field here, the consumer ID, is used to check whether this is really the reply to the answer I post. Yeah, so imagine a large network with a lot of consumers and providers. There could be some kind of problems or errors which result that the answers are distributed to the wrong consumers. Yeah? And then here with the consumer ID, I can check, does this response SPDU really belong to the request I just sent to the provider? Then similarly, the provider ID is used to check whether the source of the data, the provider, is the correct one. I mean, there could be multiple providers within one system, maybe even multiple providers of the same type, but it might be dangerous to use the wrong value for the safety decision. So you have to make sure that by checking this provider ID, that this data is coming from the right source. Then the third ID, base ID, is used to check the context of this datagram. So let's come back to the example with the wind turbines. So we saw there are many wind turbines in this wind park, and maybe for some reason within each wind turbine, I have multiple providers maybe, and maybe for some reason these provider IDs within the wind turbines are the same for each wind turbine. So maybe I have 20 wind turbines in my wind park, and then they have 3 providers, and all in every wind turbine I'm using the provider ID 1, 2, and 3, because I'm reusing the engineering project, clone this project, I'm reusing it for each wind turbine. But then there could be the problem that there is a addressing error which is going from one wind turbine to another wind turbine. For that reason, I also assign a so-called base ID or to each instance of the wind turbine. And by that I can discriminate the individual devices in the wind turbine. So these IDs here in general are used to detect addressing errors. And now here this so-called monitoring number is used to detect problems with the sequence of the telegrams or the timing of the telegrams. Yeah? So each telegram has a number, and here I can check whether maybe this is not the latest SPDU, but maybe some old SPDU which has been stored in a network storing element in a router or something like that, and by an error of the router is now popping up. And maybe this is a telegram stemming from yesterday, and of course contains completely outdated safety data, and I wouldn't want to use that in my safety application. Yeah? And by using this monitoring number, which can be understood as some kind of sequence number, I can check the timeliness of this telegram. Then here in the last field, this is a CRC checksum, and this is used to detect any data corruption which might have happened during the transmission of the telegram. So if one of the bits here in the safety data has flipped or has been corrupted or anything like that, of course, this could be very dangerous. And this is then detected using these CRC mechanisms with a very high probability. And last but not least, finally, there is another mechanism implemented within the safety consumer, which is simply checking the time which it took since sending the request SPDU until receiving the response SPDU. And there is an upper limit on that time. Let's say, for example, it's 10 milliseconds or 100 milliseconds. And then if the timer has not run out before the response SPDU is received, we know that the age of this whole data is less than the 10 or the 100 milliseconds. And clearly, this telegram here can only be generated after the request SPDU has been received, and then the age of this telegram must be here within this time. Yeah? And so I know that be able to detect unacceptable delay by using this consumer time. Okay, what exactly is the relationship to FLC now? So as I have mentioned, OPC UA safety can be implemented using OPC UA PubSub. And we have seen this request SPDU and the response SPDU, which is used to communicate. And when we are using PubSub, then these SPDUs are simply realized using OPC UA variant. So the safety provider publishes the response SPDU and subscribes to the request SPDU, and it's the other way around with the safety consumer. It publishes the request SPDU and subscribes to the response SPDU. So, and now these pairs of SPDUs can now be seen as a bidirectional logical connection. So I have simply stolen this figure here from Georg's slides, and you can see here the output data and the input data, and this pair here are then the request and response SPDU. And for that reason, you can now use the mechanisms defined within the FLC initiative to configure your safety connection. And you can also use the mechanisms defined for offline engineering to export your safety connections within your FLC information model and import it on the next controller where you want to implement. So in summary, that means we try to keep the safety configuration and the safety offline engineering as similar to standard engineering and configuration as possible. So of course there will always be some kind of specialties with safety where you have to be very careful. You have to don't do anything which may be dangerous. Yeah, so we still have this, but the principal mechanisms, how to exchange data, how to configure the connections, how to set up connections and tear down connections, and how to do offline engineering are identical if we talk about safety connections or standard connections. So that's the principal idea, to not have too many special cases. Finally, I would like to talk a little bit about the timeline. So we have now published the version 1.04 of the specification. It's controller to controller only at the moment, and only client server. So at the moment we are not able to deal with real-time communication, but that will change soon. So we are currently preparing the next part. So probably it will be called 1.05, but I'm not 100% sure about this numbering scheme here. So that's therefore I put the question mark here. And this will also include PubSub, and therefore be in principle ready for real-time communication, and therefore matches the requirements of FLC. So the technical work here is already completed, and it will now go in the so-called review of the technical advisor committee at OPC Foundation, and then we hope that we can publish this within the next few months. And then, of course, we will also talk about controller to device at the field level, and this will then be the next step. In the working group, we are not only dealing with the specification itself, but also we describe a test specification. So the specification itself describes how a device has to be implemented to implement OPC UA safety, and the test specification describes how a device will be tested for OPC UA safety. And this is, of course, very important in the safety context, because we need a good test, with a high coverage to convince the certifiers that the test really shows that device implementation is safe. And the OPC Foundation has also decided to fund a test tool, which will implement the test specification, and also a safety stack which can be reused in the device implementation. And the test tool and the safety stack, they will be provided to the vendors of OPC UA devices. They can use it. The test tool, for example, will be used in the laboratories for device certification, and can also be used by the vendors itself before they go to the laboratories to check whether the devices would pass the test or not. And then, of course, what is important in the safety context is here the certification by notified body. So we have already certified here this release 1.04, and of course all the other steps, they have to be compiled by certification. So we will certify, of course, the newer versions of the specification, but also the test specification will be certified, the test tool will be certified, the safety stack will be certified. So and we do everything, of course, to make the development of safety devices as easy as possible for the vendors to do as much pre-certification of these components here as possible, so that the effort for certification for the device manufacturers will become as low as possible. Okay, so that was my presentation. Thank you very much for your time, and I'm available to answer your questions. Thank you very much.
Perfect. Thank you very much, Max.